pictures, though.
Yeah, they're all the same picture.
Quite a few pictures, like 100 pictures or something.
Yeah. They're all of the same nature.
Yeah, people asked me what that paper was about, and I came up with like 2 different answers. One of which was, it's about understanding massive two-dimensional supersymmetric field theories.
In 2
all the
dimensions.
things you're interested in. Wall crossing and supersymmetric whatever, and BPS states. Yeah, lovely. The other one is it's applied category theory. That's sort of what it is.
Is it true?
Isn't that what it is? They use category theory. They categorize things and then use that for things, I think.
Is it true?
That was what I could tell. I didn't read through even the short version,
but there's like a ready-made functor that does the thing they need to do. Yeah, it's true.
Categorifying is I think Mura's life work.
Categorifying is the correct term.
It's his life work, you think? Huh?
So there's a functor. I just hear his talk.
Is it automated? Like, if I wanted to categorify some other thing that I like, could I just use it and it would do it? Like, can you categorify Fermi liquid?
Or love.
You're so ambitious.
I don't know. Fermi liquid, you're pretty ambitious there.
Maybe.
You think? Or you can teach me how to do this. Alright, I'm just getting my water. You ready to start? Welcome back. So it's last time I classified states of matter very coarsely, and suggested that it's a good idea to try to identify labels that we can put on states of matter so that we don't have to make sure that it's really different from all the other ones by exhaustively checking all possible phase transitions. And one class of labels that I mentioned was symmetry breaking order parameters, and I would like to regard that as a somewhat solved problem. And another class of labels that I mentioned was topological orders. I gave some consequences, some sharp consequences of what I meant by this for gapped states. I gave a general definition of what I mean by topological order, a physics definition, as emergent deconfined gauge theory, and that statement is maybe I don't know. It's not the most under control definition I've ever given of something, in the sense because it requires us to confront the dynamics of gauge fields. So this situation, I think, is a good one for giving an example, which I think will help for explaining how those consequences, symptoms of topological order that I described, arise, and showing what I mean by an example of a deconfined gauge theory. So to begin today, I want to focus on effective field theories for quantum Hall insulators. This is I guess I should confess this is a bit of a retreat up my classification by desperation, in the sense that these are in some sense they're in the category of the simplest things. They have the fewest low energy degrees of freedom. The incompressible such states have no low energy degrees of freedom, no propagating low energy degrees of freedom. And so, in some sense, this is kind of cheating, but I think it'll be a good starting point for our discussion. So I think it's worth doing. So this is 2.1, effective field theories of quantum Hall insulators. And I'm gonna give, like, I don't know, maybe 4 or 5 different such effective field theories at different levels of resolution. Excuse me one second. This is the problem with the fact that I printed my notes before I left for Boulder. Okay. And at different levels of resolution, we're going to have some energy axis like this. And at the shortest distances, there's the Planck scale of condensed matter physics, which is the Rydberg. This is the Planck scale of condensed matter physics, both in the sense that it's where the nice description in terms of a lattice model with electrons sitting on sites breaks down in favor of some fluctuating space-time foam, because the electrons can be ionized, and that lovely picture of the number of electrons sitting in their energy levels goes away. And it's also the Planck scale in the sense that you can derive it in the same way that Planck derived the Planck scale, just by listing all of the dimensionful quantities involved in the problem and making an energy out of them. Okay, so this is the scale of chemistry. So chemistry is the analog of quantum gravity in this discussion. And then, okay, so I'm going to stay below there. And at some point, there's some description, which maybe I'll just write the degrees of freedom. So I'm going to write some kind of action or Hamiltonian involving these degrees of freedom. And so here's somewhere here. There's some creation operators, annihilation operators, which will create and annihilate electrons. Okay, and somewhere down here, there's the theory of the ground states, which is where, and so lots of things are going to happen in between here, and we'll talk about many of them. And down here is the theory of the ground states, which it's kind of a theory of nothing. But the nice thing about this example is that we're going to think about a system where there's a conserved U1 current, right? Which, if you like, you can think of it as the electron number current, and that means that means that we can couple it to an external gauge field, and compute some effective action as a functional of that external gauge field. Right. So here, if I have some action for the electrons, down here the thing we're going to have is an action for this external gauge field. So curly A is going to be my external gauge field. And so the situation which I want you to think about is some stuff in 2 + 1 dimensions with a conserved U1 current. All right, so that means that the action, we can make an action somewhere in here, which governs the stuff and this external gauge field, which is the action of the stuff unperturbed by our external gauge field, plus a term which is J mu A mu. And so this is what I mean by coupling it to an external gauge field. And so this thing is the conserved current in question. And the question I want to ask myself right now is, what do we know about the form of this? Oh, sorry, there's one more step that I want to do, which is we're going to assume that our stuff has an energy gap. So here is this delta E, of which we spoke so much last time. So this is, let's say this is E = 0 here. Then if we're interested in this effective action, the way we construct it here, let's call it S effective of A. The way we construct it is in real time is by doing the path integral over the stuff of this action. Right? And so this is some functional of curly A, which encodes some properties of, it encodes the electromagnetic response of this system. And the nice thing about the presence of an energy gap is that in doing this path integral, we only integrated out gapped things, modes with finite frequency. And that means that this effective action has a local derivative expansion. Right? There's no horrible 1 over boxes in it, because those 1 over boxes all are 1 over box plus m squared, and that m squared is bigger than the box. Okay, and so it has a good derivative expansion, and so that basically means that we can guess what it is. Well, what can it be? A is a gauge field that has dimensions of 1 over length, and so we can organize this expansion by so this is a single integral over space and time, because of this locality property I just mentioned. And while the most relevant operator you could imagine is just a squared, right? That's it's the simplest thing that I guess there's some, yeah, okay. Let's assume that there's some rotation invariance, so you have to contract the indices, right? But I want to assume that our U1 symmetry is not spontaneously broken by our stuff. In fact, if it were, then it wouldn't be gapless by Goldstone's theorem, and this situation wouldn't apply. And so that means that the coefficient of this term vanishes. Right? So if it were non-zero, there would be a Meissner effect. It would be, that's a mass for the external gauge field. That's not there by the assumption that the symmetry is not spontaneously broken. By the way, something I should really emphasize here is that this curly A that I'm writing here is an external gauge field. I'm imagining that it's something that we get to pick once and for all. It doesn't fluctuate. Yes, please. Yeah. Yeah, that's right. So it's hard to have that term without. Yes. Yes, that's right. In order to have that term, you have to have an extra degree of freedom, which is gapless. That's correct. Yes. Yes, that's right. Right. So that. Yeah. Say again. You're asking if there's an anomaly. Well, so yeah, I'm assuming that it's really a conserved current, right? So if it were not conserved, there would be something here, which maybe for some perspective could be an anomaly. But yeah, I'm assuming that it's not anomalous. Right? Okay. So then the next thing that we can write down is okay. Well, so the kind of term that the kind of insulators one usually encounters would have is a Maxwell term, something like this. And I guess since I didn't assume that my stuff is relativistically invariant, really I should write this as some coefficient of E squared minus some coefficient of B squared. But let's not worry about that too much. And then dimensional analysis forces me to put some 1 over m here. Because I said we're in 2 plus 1 dimensions, and so this term is actually an irrelevant operator, according to this counting. And then there's lots more terms, but there's a very special thing about 2 plus 1 dimensions, which, for better or worse, will be kind of the star of the show for a little while, which is the Chern-Simons term, which, let me write it as, with indices. I guess I should maybe raise and lower my indices. Something like this, and it has a coefficient which here I will call nu over 4 pi. Okay. So this is called the Chern-Simons term. And it's special to the 2 plus 1 dimensions because you see that we've used all the indices in just the right way. And notice that because this has 1 derivative and this has 2 derivatives, its coefficient is dimensionless. And okay, so we're going to say some things about that coefficient in just a second. In particular, it's quantized under some assumptions that we're pretty close to making. And why might we care about it? Well, one reason we might care about the terms I've written. Notice actually, I guess I've also only written the terms quadratic in the gauge field. And one reason you might be able to think of terms that are not quadratic in the gauge field, but one reason that you might care about just those is if you want to compute the linear response of the stuff to a perturbation by this external electromagnetic field, you can do that by this usual trick of, did I say what z was? Yeah, so z is I guess I just need this effect. Maybe there's some eyes. Sorry? Oh, I'm behind the horizon. Oh, thank you, yes. No, there's no escape. Okay. I should know that by now. Okay. Okay. So this is just the usual formula that relates correlation functions to derivatives of the generating function with respect to sources. And you can imagine putting indices on here, and these things are functions of some things. So, well, why would you care about this two-point function? Well, one reason to care about it is that, for example, the conductivity tensor, of which we'll care about a particular component, which is this Hall conductivity, can be determined from this information. With a little bit of manipulation. So I guess this formula is called the Kubo formula. And it's the order of limits matters here. So you divide by omega, you set k equal to 0, and this is k, and this is minus k. And so if you know this information, you can determine the Hall conductivity, right? Just by taking two derivatives, and really those two derivatives just pick out the coefficients of these terms in here. And well, maybe I could make you do this exercise, but I think I won't. If you take that expression and plug it in here, the answer you'll get is nu times. If I were being careful about units, I would put an e squared over h here. But I guess I probably set both of those things to 1 at some point. Oh yeah, maybe the better units is nu over 2 pi. Okay, yeah, that's there's a 2 pi somewhere that. Oh, I guess that comes from this 4 pi. Okay, so the important summary of what I've said, I've written lots of formulas, but the important summary is the quantum Hall response, a non-zero sigma xy, comes from the Chern-Simons term. Okay, right? That is the equivalence that we just derived. The specialness of that coefficient can be understood a little more if we think about the following nice thought experiment. In this expression, it comes from setting h bar to 1, but I had previously also set h bar to 1, and I was wondering where it was there. Yes, you are correct. Okay. I guess let's go over here. So the following argument shows that this coefficient is quantized under certain assumptions, and so here it goes. Let's think about a thought experiment where here is our pile of stuff. It has two space dimensions. There it is. And let's imagine we do a particular thing to it, which is vary this external gauge field in time and space in such a way that we thread 2 pi worth of magnetic flux through some region in this thing. All right, so you imagine like sticking some solenoid through it and gradually ramping up the current till it gets to some particular value, such that 2 pi is the change in the whole history of the universe of the magnetic flux, by which I mean integral of b. So b is the magnetic field bit of coming from that external gauge field. This is integrated over some region R, that's R there, and the total change in the flux is integral dt of ddt of the flux from whenever to whenever. And okay, so that's just calculus and the definition of the flux. And then Faraday's law, which is really just the statement that the vector potential exists here, tells us that we can relate this to an electric field. Which is circulating around the boundary of R. Did I get that right? Maybe there's a 1 over c somewhere if you're in the wrong units. So the boundary of R is some curve like this with some orientation that's determined by Lenz's law. Okay, and why do I care about this electric field? Well, this something I didn't say but probably should have said is that, what is this sigma xy? Well, I apply an electric field in the y direction, and it produces a current in the x direction, right? That's the definition of sigma xy, from which this formula follows. And so if I have an electric field circulating around this loop, then I can relate it by this Ohm's law to the current. So this is so we're going to substitute here the azimuthal component of the electric field times sigma xy is J sub r. Right? The Hall conductivity is I apply a field this way and it makes a current that way. It's a really weird thing. And using that relation, this is minus 1 over sigma xy. There's a 2 pi. That's the 2 pi and sigma xy. No, where's that 2 pi? Oh, damn. Okay, integral dt of J sub r. Sorry. That's from the integral around the thing. Sorry. Yeah, this 2 pi is just integral d phi, right? That drops out. Good. And what is this? Well, that's the flux of the charge current through this curve, right? J sub r is the amount of charge passing through per unit time passing through that curve, and integrating that over time, that's the amount of charge that has passed through that curve. And so altogether, this is equal to minus 2 pi over sigma xy delta q. All right, where delta q is some amount of charge that passed through this thing. And so okay, this was equations in words. What it says is that in a system with a Hall response, if I try to stick in some magnetic flux there, a little patch where the magnetic field is non-zero, charge gets attached to it. Right? This amount of charge, the minus sign says that the charge is getting sucked in, actually. Though I guess if you change the sign of the Hall conductivity, it goes the other way. And so charge gets attached to the flux. And okay. And moreover, this object here that we've created by threading this flux is some localized excitation of the system. Right, so it's some object in the system, and it can move around. And if we move some other object in the system around it, say adiabatically, so take one of the microscopic constituents and move them around this object, it'll experience a Bohm-Aharonov phase from the presence of the flux. And this statement means that these two objects have some mutual statistics, which is determined by sigma xy, right? Because the amount of charge. So here, I guess I should write the final formula there. Delta q is equal to nu. Where's the nu? So it's equal to sigma xy. And so the conclusion is that this object, it has statistics angle. So bosons have statistics angle 0, and fermions have statistics angle pi. This thing has statistics angle pi times sigma xy. And so if the system in question is not fractionalized, meaning that all of the excitations of the system are still have the same quantum numbers as the original excitations. So namely, if the thing's made of electrons, the excitation should have just the quantum numbers of electrons. Then, so not fractionalized means that this object should have those statistics, and it means that pi sigma xy is pi times an integer. So this is if the system is made of fermions. And if the system is made of bosons, then the thing had better be a boson. And so pi times sigma xy had better be an even integer times 2 pi. OK, and so the assumption that the system is not fractionalized implies that the Hall response, this nu is the thing that's the integer, is an integer, or even an even integer if the system has no fermions in it. OK, and so that means to get a fractional Hall response in a gapped system, in a system with a gap, which is necessary for these assumptions, then it's necessarily they're objects with fractional statistics and fractional charge. OK. OK, so that's what I wanted to say about that. And so I guess I should say that such things exist. It's really amazing. OK, so yeah, maybe I should say this somewhere here. There exist physical systems, which are actually somewhat commonplace now, with a gap, and sigma xy is e squared over h times p over q for various p, q in the integers, and the case where p, so p equals 1, q equals 1, the case where there's no fractionalization is the integer quantum Hall effect. And this, while it can be realized with free fermions, is still quite remarkable because it has gapless edge modes. This is an example of, this fits into this category of topological insulators. And in this case with q bigger than 1, an integer is this fractional quantum Hall effect. And this is more interesting in the sense that it has at least this one symptom of topological order that it requires this fractionalization. OK, so that was the point I wanted to make here. And so now I want to show you a slightly more microscopic description of how this can arise. OK, so we're going to sort of peel back the layers of this onion of physics here, starting from here. So we're going to try to find a description of a system which is slightly more microscopic, which is somewhere, no, it's still below the gap actually. It's somewhere here maybe. Well, it's somewhere around here, I guess, which is, it's going to have 2 degrees of freedom. In addition to this, this isn't really a degree of freedom. This is this external gauge field. It's going to have another degree of freedom, which is a gauge field, which I'll call little a. OK, so this is the next goal. OK, so this is 2.1.2, which is, I guess the subject is really abelian-Chern-Simons theory. OK. So I want to explain how this fractional statistics of excitations and topology-dependent degeneracy of the ground state can arise from a field theory. That's the goal. And so here we go. So forget about the external gauge field for just a second. Think about the following system, which is, so this AI is a collection of abelian gauge fields. This runs over some small set of values. Okay, so I will occasionally, I've written this in terms of forms. Really what I mean by this is what I wrote over there. Epsilon mu nu rho, AI mu, d nu aj rho, right? And notice that this is an action we can write for gauge fields in 2 + 1 dimensions. This is in 2 + 1 dimensions on any whatever space you like. It's an action we can write for gauge fields without ever introducing a metric, right? So I didn't have to say anything about contracting indices or anything. The only thing I used to contract the indices was this epsilon tensor. And so in that, already in that sense, it's a topological field theory. And let's see what it does. A question you should be worried about is where did this gauge field that I'm talking about come from? From the it somehow emerged out of this mist here. We'll come to that. Okay, so don't worry about that right now. Let's just think about what would happen if we got this answer. And okay, and I guess maybe I have to mention that there are two more ingredients in this story if we want this to be a possible effective field theory for a quantum Hall insulator in some regime of energies, which is I need to tell you how to couple this to the external gauge field. The way I can do that is by telling you what J is. And remarkably, this thing has conserved currents. It has conserved currents because epsilon mu nu rho d nu a rho is something which, if I'm trying to be good about my upper and lower indices, mu nu rho. So this is an object, which here we can stick an I here. Maybe we could even take linear combinations of them. So whatever I pick for J, this is some J with one index, which is here. If I take the divergence of this object, what happens? It's 0, because this thing is anti-symmetric, and if I have two derivatives, it's symmetric. Has d mu j mu equals 0, and for any t. And so I can specify some coupling of the system to external gauge fields just by choosing some set of t's, and there you go. So this thing is sort of some amount of magnetic flux, which is the charge density of this thing is the magnetic flux of these gauge fields, and it is a conserved quantity. Okay, the other ingredient I should mention is there's some remnant of the stuff above the gap in this system. So I said it was an effective field theory somewhere in this regime, and that means that it knows about the gapped quasiparticles. It knows about things that happen right at the gap, and that information is encoded by saying some set of currents that are coupled to these gauge fields. So that is, there's some additional information which is about the quasiparticles. Which, all right, let me just add it in here, which we're not going to worry about too much, but it's some recognition that there can be some set of currents that are minimally coupled to these gauge fields. Okay. Okay, so here's a homework problem for you. If you take this expression, so I guess I could be, what? Let's just do it all at once. There we go. And add to it this external coupling to this external gauge field. What did I call this? This is let's call this J external. External. So with this action, this action is quadratic in A, right? A appears twice here, once here, and once here, and so you can do the integral over A with this action that I've written here. Set this to 0, and the answer is you get some answer for this this guy here, and by our assumptions it should have that form over there, and so it predicts some coefficient for this Chern-Simons term for the external gauge field in terms of this information. Okay, so that's an exercise you should do, maybe not right now. So all I'm saying is integrate out these gauge fields and find the effective action for the external gauge field. You're asking me what k is? Well, you can do this calculation for any k, right? I haven't told you what k is, right? Okay. Maybe. Yeah, so you're okay. I guess it's a fair question since I'm asking you to actually do the path integral over A. I should tell you what we're integrating over. But actually, well, okay, I guess I should say you are absolutely right that there are occasions when the well-definedness of a Chern-Simons gauge theory requires some quantization condition for this K. And certainly, the answer that you get for sigma xy, it's, I don't want to tell you the answer, but it's, it's determined by K in this calculation. And so here, I said that if there's no fractionalization, it has to be an integer, right? So that will certainly put a condition on K and on T. Now, in the case where there's some fractionalization, which in this theory in general will demonstrate, it maybe isn't so clear that Q has to be an integer. Maybe it could be square root of 2. And then we would get some particle with statistics angle square root of 2. Maybe that's okay. I think actually, I don't know if there's a physical realization of that, but I don't know a consistency argument against it. Yeah. Yes, please.
Sorry, what's the little JQP?
Yeah, that's a good question. It's I've been somewhat mysterious about it because it contains some information about the physics above the gap. So I want you to think of it. It's some conserved current made of massive stuff.
It's like a classical thing we're adding, or is it a degree of freedom integrating?
It's some other massive degree of freedom. Yeah, that's right. So in the full path integral, it fluctuates. But so in this calculation, I want you to imagine putting it in its ground state, in which case you can set that to 0. Yeah. I'm going to come back to what this is.
That's right. From an effective field theory perspective, why didn't we include something that has 3 Ks? Is that not?
Good question. Okay, so let's see. So from the point of view of computing so you mean this A?
Yeah, let's say whichever.
Well, so for the reason I didn't include such a thing in the effective action for the external gauge field was because I was interested in the linear response. Which, oh, wait, did I? I totally, jeez. Right, so if we're interested in the linear response around no field, then I should set this A to 0 at the end. And so the cubic term will go away in this calculation. Right, so that's why I didn't include it there. Why didn't I include it here? Well, we could try to include some just you mean like A wedge A? Hey, well, so okay, if we have only one gauge field, that's 0 because of the antisymmetry. Isn't it because it's what? Well, you're right. Then in the non-abelian case, there is such a term. Yeah, I guess I should. Yeah, that's why I wrote the word abelian. That's important simplification. Yeah, it would make it into a non-abelian theory if you could write such a thing. Yeah.
It's not gauge invariant for different gauges.
Yeah, in general, it's not gauge invariant. That's right. So I am imposing a gauge redundancy in the system. Okay, so let me make another very important point about the system, which is about another quadratic term that you might be interested in adding here, which is what about Maxwell? Right. So I've sort of already given away the punchline here, which is that suppose we consider just the action for one of these gauge fields. So let me just write it as little k, ADA, and then add to it a Maxwell term. I don't know, let me call it M naught dA squared. Right, so this is an irrelevant operator, but what does it do? Let's figure out what the propagating degrees of freedom are with this action. So if I compute the propagator, I guess this is basically what you have to do this calculation anyway. The propagator for this gauge field, I guess let me write it like this. I will carefully hide all of my indices. So it's 1 over, so this is, let me imagine that this is in momentum space. And let me pretend that it's relativistic. Is something like k over 4 pi. There's an epsilon and a k. I shouldn't use K for the momentum, should I? All right, so let's call it Q. Epsilon Q. All right, so it's a puzzle to figure out where the indices go. Right? This has three indices, and that has one. And then we add to that. So I'm just inverting the thing in between the A's here. Plus 1 over m naught Q squared. Right, and then I guess there's two more indices somewhere. Okay, where does this have poles? Right, at what frequencies and momenta does this have poles? Well, there's one at q equals 0. Right, if I just take q equal to 0, the indices kind of matter a little bit here. So it's something like 1 over q times this is a cartoon of an equation that I'm writing here. 1 over q, and then something like 1 over q k over 4 pi epsilon plus 1 over mq. Right? So if you pretend that there's no indices here, then I'm factorizing this polynomial. And so there's a pole at 0, and a pole at q is something non-zero, proportional to m naught times k. Right? So this vanishes at q is m naught k over 4 pi with some epsilons. Okay, so something you probably know about Maxwell theory in 2 + 1 dimensions is that it has only one polarization state. Right? There's only one propagating degree of freedom. If I only had the Maxwell term, right? If this were gone, if k were 0, right? Everybody agree? Right? Because there's only one transverse dimension. Okay. So this thing has two poles. Which one is the one that comes from the massless Maxwell theory one? The answer is it's this one. And this one is a kind of is not a propagating mode. Careful accounting of the indices shows that the propagating part of it is a gauge redundancy. And so the conclusion of this cartoon of a sketch of a calculation that I've done here is that the Maxwell term gives a mass to the gauge field. Right? So I guess when this was first discovered, it was called topologically massive gauge theory. And it's really an interesting and different way of giving a mass to the gauge degrees of freedom than just adding an a squared term. Right? Because we did it in a way which keeps the same number of degrees of freedom. Right? We didn't add a Goldstone mode and then eat it. Right? So in some sense, this is like describing a confining state of the gauge theory. Except I don't want to use that word because there is a strong sense in which there is still deconfined gauge dynamics. It just doesn't involve any propagating vector particles. Okay, so the conclusion of this discussion is that the Chern-Stearns term gives a mass to the gauge theory. And in the limit where we take m naught to infinity, so that as we look at energies much lower than the scale here, then cross this out, we're taking that mass to infinity. Right? So the propagating mode in that limit goes up and away. And so that's the limit we're going to think about, which is this topological field theory. Okay. So now a calculation which is basically the same as the one I did here, this Laughlin thought experiment kind of thing. I think that's due to Laughlin. But now in this model is the following, which shows that this has anyons in general. Okay. Suppose we forget about the external gauge field for a second, set A to 0, and think about some fixed configuration of that quasi-particle current. So I want you to imagine that we stick a single massive particle which carries the charge in question. Okay, so let's think about S of A equals 0. I guess I should have probably said that this is a functional of this quasi-particle thing. So this is epsilon over, I'm in the black hole. Okay, epsilon over 4 pi k over 4 pi epsilon AdA plus A times this quasi-particle current. I'm just rewriting that again with A equals 0. And now look at the equations of motion for the Chern-Simons gauge field. It says this F is dA, little f is little dA, k k over 2 pi from the fact that there's two a's there, plus this quasi-particle current, is 0. And so this is the analog of the Maxwell equation for this Chern-Simons theory. But what it says is that the flux just gets attached to the quasi-particle current. So if I have a particle there, it says that this dynamical A gauge flux, this thing that's actually the conserved current, just gets stuck onto it with a coefficient which is determined by this coefficient k. Okay. Okay, so this says that flux attaches to charge, right? It's the opposite statement here, right? It says that the Chern-Simons flux gets attached to the charge, and so in particular, I guess this is really three equations. Let's look at the time component of this equation. It says that I guess I can call it B is the okay, let me write Fij here. Here we go. Epsilon ij Fij is B. That's the spatial components of this F. Gets set equal to 2 pi over k times the quasi-particle density, right? So rho is the time component of this J. Okay, and now let's think about what happens if we take one of these quasi-particles. So this is a particle, which is a delta function source for that density, and circle another one around it in some path C. So this is another one. Then let's think about the phase of the wave function of this guy. I guess let's call them 1 and 2. The change in the phase of the wave function of that guy is, well, it gets a phase. It gets a yes, please. It might not be. Oh, yeah. Good point. Okay. Yeah. It's fixed by an epsilon, and the question that we need to ask ourselves is where we want to put it. Let's put it here. By the way, I've something a contribution to science that I've made, which I highly recommend. It's maybe my most important discovery, is that when you're contracting tensors, and you're contracting a lot of indices, and you're not planning to do horrible manipulations with them, it's useful not to give them names. I think it's a big, important contribution, right? That you know that you have to contract this one with this one and this one with this one, and just keep them in the same order. It's not okay. So anyway, so thank you for asking this question. To give me an opportunity to impart upon you this wonderful gift. Okay. I think maybe if you're doing some horrible general relativity calculation where your tensors are not all completely antisymmetric, you might get in trouble. It's just possible. But for topological field theory calculations with forms, it's the good stuff. Okay, so let's think about the experience of a single quasi-particle here. So this guy is also a delta function of this. So the state I'm considering is rho quasi-particle. X is a delta at x minus x1 plus delta of, I think maybe I even gave them a name. This is Q1 and Q2 delta of x minus x2. And I'm imagining that I'm a giant hand that can grab this thing. So at the moment I'm thinking of this as an external current that I can control. I'm imagining adiabatically moving this around. Okay, so adiabatically means that everything is as slow as possible. The only thing that contributes is this topological Berry kind of term. And so this is Q1 times the integral of the A that it experiences around this curve, and which is Q1 times an integral over a region whose boundary is C, which I think you can guess which region I want to pick, of B. This B is this B, which, using this equation, picks up a delta function at the origin. And so these quasi-particles have a change in their mutual statistics compared to what they would have if they were not coupled to this Chern-Simons gauge field, which is determined by K. Okay, so these excitations, if you stick in some excitations coupled to this Chern-Simons gauge field, their statistics are transmuted by an amount determined by k. Okay, so these are the fractional excitations whose existence is guaranteed by this argument. In the case when k is bigger than 1, so k bigger than 1 will imply q bigger than 1. It's a hint for the answer to that calculation. Okay, so this was symptom 1, I think, of topological order. And then symptom 2 was about the topology-dependent ground state degeneracy. That's bad form to hide that right now, isn't it? Okay, we'll come back to you. Do a little squeegeeing. Ask me some questions while I'm squeegeeing. Do you guys all know this? There's some sector of the world where everybody knows this. Are we not in it? Say again? Thank you for saying that. Okay, good. Does it matter the time? Oh, I should have left this. The time delay between squeegeeing, between the wetting and the squeegeeing.
You've become an experimental.
Well, I guess we can try. Yeah, let's see. Okay. It's better to start on top. Because gravity points down. Yes. All right. Yeah, I think that's contributing to the success of this. Yeah. Okay, so topology-dependent ground state degeneracy. Let us take our Chern-Simons theory. Let's do the simplest case again. And put it upon a Riemann surface of genus G. What do you think? Maybe we'll do genus 1 first. I don't know. Let's do genus 1 first. Yeah, let's do genus 1 first. Okay, so this is the action. Let's do just a single one. Okay, and so there's one of the terms in here. Let's write this out a little more explicitly. One of the terms in here is the term where one of these guys is 0, in which case the other guys have to be space. I guess I called this B. Maybe there's a coefficient here. Maybe there's a 2. And then, well, actually, here, you know what? Let's include the quasi-particles. Well, okay, so, yeah, fine. And then there's another term which involves time derivatives, where there's a dt of ai, right? And so if that's an a, this is t, this is I, then this is the other one. And so then this is epsilon ij, aj. Okay, so there's maybe there's some 2 here, and maybe there's some 2 here. You guys can figure that out. And each of these 2 terms is quite informative. This one says that A0 is a Lagrange multiplier that sets B to 0, right? And that's because we set the quasi-particle current to 0. That's just this equation again, right? So this equation is the Gauss law for this funny gauge theory. And let's take advantage of the gauge symmetry and set A0 equal to 0. Okay, so we can forget about this term. Its only role is to impose the Gauss law. And then the other term is even more informative. It says that the canonical momentum for AI, right? That's what we usually think of as. It's not an opinion. It's the canonical momentum for AI is the other one, is epsilon ij aj. With a coefficient, it's an important coefficient, which is k over. There's definitely here. There's a 2 pi. I think. I better get that right. That 2 pi actually matters, and I probably got it wrong. Yeah. Okay. Well, if we get the wrong number of ground states, that's wrong. Okay. So it says that the canonical momentum for one of them is the other one, right? And we can add a total derivative term to mix, which is the one that has a canonical momentum. Okay, so it says that in canonical quantization, ax of x, this is okay, with ay of y, this is an equal time canonical commutator. These guys have hats now. Is a delta function. Oh, there's an I. There's an I. Oh, damn. Okay. Well, I'll get it right. I'll get it right. X minus y in 2 spatial dimensions, and then there's a 1 over k there, right? And a 2 pi. And how did I do? I think the I is wrong, but otherwise it's right. Right. So it says that basically these two things are like x and p. Right. So actually, if you integrate, if you study the 0 modes of these things, they're exactly like x and p, right? They're canonically conjugate variables, except that you need to put a 1 over k there instead of an I. And, well, okay, actually here, string theorists are supposed to know about Riemann surfaces, right? So you know that on a Riemann surface of genus G, there should be 2G 0 modes of 1 forms, right? The Laplacian acting on 1 forms should have 2G 0 modes, right? This is like the Riemann-Roch theorem or something, right? I knew things like this at some point. On the torus, it's just the thing I said. You integrate ax over x, and so this is ax 0, and integrate y over. Oh, sorry, I have to integrate over both the dimensions, and integrate y over this guy, y0, and these things satisfy with no delta function, right? And so the ground state of this system has to represent this algebra, right? Because these, something I should, okay, so we derived the canonical momentum. I didn't derive the Hamiltonian. Somebody tell me, what's the Hamiltonian? It's 0, right? It's the system with first order time derivatives and nothing else. So the Hamiltonian is just 0. So anything we can do to change the state produces another state with this 0 energy. And so the ground states, the set of ground states have to represent this algebra. There's kind of a nicer way to write it. So actually this, this stuff, ignore this, because the better way to write it is to construct loop operators. So instead, consider f sub, let's call them f sub x, is e to the I integral a over a curve which goes around the x direction. Okay, so here we go. Here I can do my fancy thing. So pick a basis of 1 cycles on the Riemann surface. Yeah, here we go. Good. I knew I could do some fancy thing here. So here's my Riemann surface. It is a luxurious many-hole donut. Okay, that's not that many, actually. Okay, so we can pick a basis of cycles, which there's a bunch of them that look like this. And there's a bunch of them. I've run out of colors. Ooh, okay, hold on. I'm going to use this eraser. There we go. It kind of works, right? You see, yeah? All right. Well, I think you know what I mean. So there's a bunch of cycles, which let's call them A alpha and B alpha. Right. So each of these goes from 1 to G, which is the number of handles of my donut. And let's call this f sub A alpha, and f sub B alpha, which is e to the I integral of B alpha. And then a wonderful and fun calculation that each of you can do in your spare time is to show that each pair of conjugate loop operators associated to a pair of conjugate cycles which intersect each other satisfies a Heisenberg algebra. That is, FA alpha, FB beta is not quite the same as the things if you multiply them in the other order. E to the I 2 pi over k times a delta alpha beta. Did I get it right? I think I got it right. Looks pretty good. Okay, and so the ground state, the space of ground states of this theory has to represent this algebra, and the simplest case is if it's just a torus, in which case there's just one pair of these things, in which case this is the clock and shift algebra, which is represented by, FA is 1 omega squared, and FB is 0, 1, 0, 0, 0, 1, 1, 0, 0. All right, so these things satisfy omega to the n. Satisfy this algebra on a three-dimensional space of states. That 3 is k. Right, so this is for k equals 3 and g equals 1. The number of ground states is 3. And there is no smaller representation of that algebra. You just can't do it. And so this thing gives a topology-dependent ground state degeneracy. So sigma g is, so in this case it's just k. We have one of these pairs of Heisenberg things for each cycle. It's k to the g. More generally, it's the determinant of the k matrix. Absolute value. It's positive number to the g. So where k is that matrix there. And you can see this just by diagonalizing k. K has to be symmetric. And so you can just do this for one pair of eigenvalues at a time. Did I say the right thing? Yes, symmetric, yeah. Okay. So this very simple theory, just a Abelian-Chern-Simons theory, just a Gaussian theory, exhibits 2 out of the 3 symptoms of topological order that I advertised. All right? I like it. Okay, so now further into the onion. A question that has remained unresolved in this discussion is, how could it be that from some simple model of patches of SOD, where the Hilbert space is just perfectly well-defined tensor product of a local Hilbert space at each site, tensored together, everybody knows what Hilbert space they're living in, there's no question about whether you could define the entanglement entropy between bipartitions of it. How could such a system emerge this kind of gauge theory? Right? How could it be that at low energies we get some system where, I used Gauss's law, A0 equals 0 constraint there, and there's gauge fields, there's gauge redundancies. The Hilbert space, you might think that the Hilbert space is not locally defined. Okay, so let me show you that that's possible. And I'm going to do that first in the sort of what is now rightfully the canonical example of this, which is we're going to emerge Z2 gauge theory from a pretty generic spin system on a pretty arbitrary graph. So now, when some people talk about the thing I'm about to talk about, they'll emphasize the fact that this is a beautiful solvable model which has lots of wonderful properties, and that's true. And in that context, it's called the toric code. It's called a code because it hides some special space of states, which is the space of ground states. And all that is true and lovely, but a point I would like to emphasize is that actually, wonderful. Okay, is that actually it arises in a whole open set of the phase diagram of a pretty generic spin system, collection of spins interacting in a not too crazy way. There have to be big ring exchange terms, but it's a phase. It exists in an open set of, add whatever perturbations you like. And, it's not that crazy. It's the kind of thing that you could almost imagine governs interactions between spins in an insulating solid. You could almost imagine that. Okay. And its low energy physics is described by Z2 gauge theory. All right. So this is a different system than the one I was talking about here. It's going to have a 2G here instead of a G if you put it on a Riemann surface. I'm going to come back to a description of how these very gauge fields can arise from a more microscopic description a little later. That's part 2 of yeah, I think this is right, of whence the gauge fields. This is part 1. I guess I should put the question mark there. It's a question mark. Okay, so all right, so consider an arbitrary graph. I'm doing a generic graph. Yeah, so really it doesn't matter in this case what graph you put on. Though the only thing you need is some notion of who is a plaquette. So it's actually, the thing I'm specifying is not really a graph so much as a cell complex. So in the sense that there are points, there are vertices, and there are edges, and the edges know which vertices are at their ends, right? And the vertices know which edges are ending on them. And there's one more ingredient, which is that there's faces. And the faces know which edges are on their boundary. Okay, so I don't know, do you guys like it when I say all the mathy words? You like it? Yeah. Okay, so it's a cell complex where I have a map. I have a map which is a boundary map, which takes the p cells to the p-1 cells. And for the Z2 case that we're going to talk about here, we don't care about the orientation, but more generally, the some cell here, knows about this, this is some linear combination of it's some formal sum of some elements in the space of cells with one fewer dimension. Okay, so that's the situation. It's just the square lattice, okay, if you want. But yeah, so really this model can be defined very, very generally. And the ingredient that we're going to start with is on associated to each one cell, which just means edges. I shouldn't draw there. Associated to each of these edges, we're going to put a qubit. Okay, there's so the Hilbert space is tensor product over links in, I guess they're in that, I don't know why I used the fancy letter. Okay, yeah, this one space of 1 cells of a spin 1/2. The rotation symmetry is just broken. It's just a qubit. Okay, and the Hamiltonian is a lovely Hamiltonian motif, which is a sum over sites, sum over 0 cells of a term which is called the star term. And we could put a coefficient here. Let me call it gamma E. And a sum over plaquettes, that's elements of the 2 cells, which let's call this coefficient gamma M, B sub P. And A sub S and B sub P are made of operators near to the site and plaquette in question. A sub S is, so if this is S, then A sub S depends only on those links. A sub S is a product over links in the vicinity of S. So the vicinity operator is a partial inverse of the boundary operator. It just means the links that are nearby. Of Z sub L. And okay, this I didn't come up with, but I'm very proud of propagating it. This Z sub L is the name that people with poor eyesight use for sigma Z. Right, so sigma Z acts on a 2-state system. Acting on up, it gives up, and acting on down, it gives down. And it's very important to with a minus sign. It's very important to distinguish this from sigma X, right, which in contrast exchanges up and down. And the most important information that's being conveyed by the symbol is whether it's an X or a Z. And so why should we hide it in the superscript like that? So this is actually a contribution from the quantum information people to just write a big giant Z instead. All right, so there we go. So that's what the star term is. It's the product over this link, this link, this link, this link of all the sigma Z's. And the plaquette term is associated with the plaquette, naturally. And it's the product of the sigma X's. So that's a term familiar from lattice gauge theory, right? So here you can see where the lattice gauge theory might be about to appear. It's a sum of the links in the boundary of this thing of X. associated with that link. Yes, please. Links. It's a tensor product over links in one cells. Yeah. So the spins are living on the links, right? Yeah. Okay. So is it clear what the definition is? It's really very well defined. Okay. So now let us proceed to deduce some properties of this wonderful system. The first thing to notice is that these two operators commute with each other for any choice of S and P. And the reason that this is true, the reason that those of you who have studied lattice gauge theory know that this is true, is that this term is the plaquette operator in lattice gauge theory, and this term is the Gauss law constraint. This is the operator which is set to 1 by the Gauss law constraint in Z2 lattice gauge theory. And so the statement that the plaquette operator is gauge invariant is the statement that these two things commute. Okay, so that's the good reason that they commute. And the bad reason that they commute is if you look at an S and you look at a P, then this thing has a Z here and a Z here, and this thing has an X here and an X here, and they share an even number of things that anti-commute. Right, X and Z anti-commute, and so if you have two of them, they commute. And so they commute. So that's the reason they commute. Okay, and so this Hamiltonian, I emphasize that I advertise this as a phase of matter, which is governs a large class of interacting spin systems. We're starting with the solvable point, right? This is a very special limit in the space of possible couplings between these spins, which is a sum of terms which commute, right? And each of these terms also squares to 1, right? Because it's made of a product of things that squares to 1. And so we can find this complete spectrum of this Hamiltonian by diagonalizing these terms one at a time. All right? And so let's do that in a limit where, just for convenience, because it's the limit where it looks more like lattice gauge theory, let's suppose that the star term is more eager to be satisfied than the plaquette term. Right? So we're going to satisfy them all, but let's satisfy the star term first. So it's worse to violate the star term. And so let's think about which configurations satisfy A sub s equals 1. And a nice way to do this is to go to the sigma z basis for each of the links and make a definition that for each link, I will say that if I don't draw anything, that says that z is equal to 1 for that link. And if I do draw something, is equal to -1. Okay, so it's just a graphical representation of the two states in z basis. And okay, so now we can proceed to think about configurations of a plaquette of a star which do or do not satisfy the star condition. So the star condition is that the product of the 4 links around the site is 1. So that means that there have to be an even number of them, which are -1, right? If the product of these things, yeah. Okay, so I could draw nothing. I could draw this. I could draw this. I could draw this. Those are all okay. And those get a check mark. All right, and okay, what about this one? No. And also bad is that one. Right? So these are not okay. All right, so what do these have in common that these do not? Right, there's an even number of string segments ending at this point. And this one is a little bit confusing, but if you ignore this one, it's very tempting to think of this as the condition that this is a string which does not end, right? That it continues its existence either going that way or going that way. And here it's 2 strings that are crossing, right? So in each of these cases, a string is ending. Okay, and what is this? Well, okay. So the condition that A sub s on a state equals 1 has eigenvalue 1 for any s. So that we want this to be true for all s in order to find the low energy states of that Hamiltonian. It says that that state is a superposition with some wave function of states which are collections of closed strings. The amplitudes of these things have not yet been determined, but this eigenspace of A sub s with eigenvalue 1 is the space where this thing, these are closed string configurations. Okay, and so what are these strings? So here we can make the connection with lattice gauge theory more explicit. actually, the thing I'm about to say is really just notation, but it's a very useful thing. I urge you to think about sigma x. Maybe I should put this equation in quotes, but I won't. As an integral over a fictitious gauge field, which isn't really there because it's in between the sites of the thing. So this is over a link, which let's say it's connecting sites I and j. An integral from I to j of this gauge field. All right. So this is I don't know. The equations I'm going to write in this box are cultural, let's say. And so with this definition, if this A were really a gauge field and it were governed by a Maxwell term and not a Chern-Simons term, it would satisfy, A with the electric field is equal to I. Right? This is the canonical commutation relations if there's a Maxwell term. And so the statement that sigma x and sigma z don't commute is some statement that I should think of sigma z over the same link as e to the I pi times the electric field over that link. Right? The pi is so that using this equation, these two things, this and this satisfy. Oh, why did I write sigma? I did it again. I violated my rule. Okay, that's an x. That's a z, and a big honking z. And so these equations say that x and z anti-commute. And okay, and with this notation, we also see that the plaquette operator, which is a product of x's around the plaquette, becomes integral of a around the closed loop, which if while we're pretending, I can write this as integral of b over the plaquette itself. Right?
Was there a distinction between integral on the top exponential and sort of subscript ij on the electric? Is that
here
also integrated from ij?
Yeah, good question. There's some better way to do the fiction than let's see, 1 second. So here, so I guess let me say it a little more precisely what I'm doing. I'm pretending that I have a U1 gauge theory, which has somehow been broken to some Z2 subgroup, and this A is the vector potential for that gauge theory, and this E is its electric potential, so E should be the problem is that in different dimensions it's a different thing. No, it's always a vector. Sorry, E is always a vector. Yeah. So it's I guess it's integrated. Yeah. Okay. Yeah.
John, you're at 5 o'clock. This seems like a pretty intriguing story. I don't know.
What time am I supposed to stop? I'm supposed to stop at 5.
You can students
Okay.
Students on 5:20, so we don't want to.
Okay. Good. The conclusion of this discussion is the statement that these lines that I'm drawing here are lines of electric flux. Right? That's the end of this story. It says that the electric flux is equal to 1 as opposed to 0, right? Along that edge. And so the statement that these loops are closed is the statement that lines of electric flux have an integrity, right? They don't break. Right? The statement that lines of electric flux don't end is the statement that if there's a Gauss's law, that there's no charge, right? Okay. There's no charge in the vacuum. Finally, the final thing that we need to do to understand this thing completely is understand what is the condition within this subspace of states that satisfy the star condition. What is which of them satisfy that the plaquette operator has eigenvalue 1 as well? And can I do this? Yeah, okay. I think I can do this. This will be my final blackboard. Okay, and here's the conclusion. So what does x do to a sigma z eigenstate? Suppose here we go. Suppose I take an x associated with a link, and suppose that the link has nothing on it. What do I do here? I draw the link, exactly. Right, good. So now if I have a configuration where there's no strings at all, and I act with B, what do I get? No, just one B. Just one B associated to a single plaquette. Yeah, I just get a string where the plaquette is. right? And if I act with it where on the state where the plaquette is already, what happens? It goes away. That's right. So B is both the creation operator and the annihilation operator for these strings, for a string on a single plaquette. Because it's Z2, right? This is because of the Z2 property, exactly. And so what is this? The configuration, the state of the closed strings that satisfies this thing equals 1 for every plaquette? Well, the condition that BP on psi equals psi, in terms of this basis here, this expansion of the state, it's a condition on the wave function. It says that psi of C is the same. It's the same wave function for a C and for a configuration that I can get from C by adding the boundary of some plaquette. Right? Because acting on this thing on a configuration C, this creates this extra plaquette, and acting on this configuration, it annihilates it. So this is a homological condition, right? It's an equivalence relation on our wave function. It says that the wave function is only non-zero on closed one chains, right? Yeah. That chain means closed. Very good. Yeah, cycle, right. So closed one chains, meaning one cycles. And this equivalence is the statement that it's the same thing if the thing is in the image of the boundary map. Right? So this is exactly the definition of H1 of this cell complex with coefficients in Z2. So in particular, in the case when our space is simply connected, when you can get any curve from any other curve by this sort of accretion of plaquettes, then there's just a single wave function, which is just the uniform superposition of all closed strings. And if instead the space has one cycles, like here, then this one cycle you could never get by adding plaquettes to that one cycle. Right? Adding local plaquettes to this one cycle, you can never get this one. And so they have independent wave functions. Right? You can pick a different psi for this one than you do for this one. And so the number of ground states you get is just the dimension of this space. Okay, so this is... Okay. All right, so this I guess I didn't show that clearly that this is a gauge theory. I did show that it has topological order, right, in the sense that it has a ground state degeneracy. We can make a more explicit connection with gauge fields in the continuum, which we'll do next time. And in fact, it's possible to write this as a Chern-Simons theory. It has a number of other properties which are worth noting. In particular, I want to say something about where it sits in the phase diagram. Okay, and then we'll describe a slightly less perfectly glisteningly well-defined way to realize gauge fields in condensed matter next time. All right. Okay.
Code, I've never seen it done out before. It's really simple. Now I gotta understand why it's the way they do it. Very nice. Very nice. Yeah. What's the other about it? It's inevitable. Yeah. I mean, it's a nice gauge theory with a Benjamin term and a Gauss's law term. Yeah, the important thing is that the Gauss's law is fundamental. Right. So the constraint is only on the lower end. So below this this scale guarantee. This is known as massive charges, but massive sector. Yeah.
What's wrong with
Sorry, what happened?
So it has like this guarantee that are not okay because
That violates the star condition at the middle side.
yes, that's right. So it could be a minus, but
That's an excitation.
if there's two of them.